Hello everyone, welcome to CSCE 317 Lecture 10. Today we're talking about I2C. This is something that I introduced previously, and today we're going to give it a more thorough treatment. By now you know SPI has a limitation in that it only supports having one master. And this is because all the wires in an SPI bus have a fixed directionality. You know, the master drives is the only driver for the clock, is the only driver for MOSI, and is the only driver for the slave select. This is designed to prevent double driving wires, having multiple devices or endpoints on the bus, trying to inject a bit into any wire at the same time. Now there is one caveat to this. As we discovered in Lab 3, when you use SPI in multi-slave mode, non-daisy chain multi-slave mode, where you have individual slave select wires, MISO is a shared connection amongst all the slaves, and so the slaves have to be careful to not drive or to disconnect themselves from MISO whenever they are not participating in a transaction. Otherwise, even in this situation, there's a potential there for multiple slaves trying to put a bit onto MISO at one time. This slide shows what I mean by that. You've got MISO being an output of the top slave here and the bottom slave here, and so they're connected together, shorted together. And if this MISO were trying to if the top slave were trying to drive MISO and the bottom slave were trying to drive MISO, it would be problematic. This is a problem because SPI uses push-pull style drivers, meaning that the outputs, so let's assume for a moment that we're talking about MISO. So let's say we have two slaves and they're both have an output called that's MISO, and they're both of their outputs are connected to the same physical wire. In other words, they're shorted together. So the outputs in a push-pull style interface are connected to the output of a driver, which is essentially a logic gate, like this inverter that I'm showing, meaning that the slave injects a bit out onto MOSI by turning on this top transistor to pull the output up, or to short the output to VDD, its power supply, or by turning on this bottom transistor and shorting the output to ground, or pulling the output down to ground. Right? The problem is that there's a risk that if one of the devices attempts to pull its output up by turning on the top transistor, and the other device attempts to pull the output down by turning on its bottom transistor, then you end up with a low impedance connection between the power supply and ground. That would be through the pull up transistor of one endpoint and the pull down transistor of another endpoint. And remember, these transistors are basically switches that in CMOS design they're either on or off. When they're on, they're equivalent to about an ohm. This is a problem because each of the outputs connected to an SPI bus use push-pull style drivers, meaning that each of the outputs onto an SPI bus is connected essentially to a logic gate, which can either pull up its output to a 1 or pull down its output to a 0 by essentially shorting the output either to VDD or ground by turning on pull-up transistors or turning on pull-down transistors, and then of course turning off, if it's pulling up, it would turn off the pull-down transistors, and if it's pulling down, it would turn off the pull-up transistors. Okay, so for example, assume you have a multiple slave SPI arrangement that is non-daisy chained, where you have individual slave select or chip select signals, as we did in lab 3. In this case, you have multiple slaves that are outputting their outputs, or MISO outputs, are connected to a shared wire, one conductor, one net, as I show here. Now the problem is that if this slave on the left decides that it wants to inject a 1 onto its MISO output, then it would pull up the output, meaning it would turn on this transistor, the pull-up transistor. It would short the output, which would short the output to ground, to VDD. Sorry, which would short the output to VDD. Okay, through here, and it would turn off its pull-down transistor. And then let's also assume that the other endpoint, the other slave, is trying to pull its MISO output down to ground, so it would be turning on its pull-down transistors and turning off its pull-up transistors. This would create this low impedance path from VDD to ground. So you'd have this VDD connection in one endpoint, a ground connection in the other endpoint, and then they would be connected through this shared wire. When these transistors are on, they have a resistance, let's say about 1 ohm. Usually I think it's even less, but let's just assume 1 ohm. And if that's the case, then basically this is connecting. This is a 5 volt connection over 2 ohms, which it would source 2.5 amps, assuming that the power supply was capable of providing that. Luckily, these boards that we're using are limited to 500 milliamps or so from USB 2 power delivery. So this might not cook the chips, but it would cause a voltage drop that would it would cause a system-wide voltage drop that would grind everything to a halt, most likely. So this is bad. So in order, the only way to connect multiple push-pull drivers to a shared wire is to use TriState buffers, which are these triangular things I'm showing here, which would allow the slave in this case to disconnect its MISO from the shared wire when it's not participating in a transaction. So these TriState buffers, I show like a little legend down here. Basically, these are 2 transistors that are connected in series that allow one control to totally disconnect or to connect two sides, the input and the output. The reason why there's 2 transistors here is because the PMOS style transistor, the one with the bubble here, is more effective in passing ones, and the NMOS is more effective in passing zeros. And when I say more effective, I mean the effective resistance is lower for those specific cases, for those specific types of transistors. So this is just an electronic, disconnect, essentially. However, in order for this to work, the endpoints need to know exactly when they can turn on these tri-states, when it's safe to do so. And in the case of SPI, they know that because we have a way to do arbitration by essentially having the master dictate to tell them explicitly when they are part of a transaction through the slave select signal. So that's why this works. That's why they're able to avoid double driving a shared wire. Now, an alternative approach, which is used by I2C, is to use an open drain style interface, and this essentially is a way to make it safe to have 2 outputs connected to one shared bus. So the way this works is that the endpoints only have pull down transistors that can take the output and connect it to ground when they want to send a 0. Otherwise, they turn off their pull down transistors and the bus is then pulled up to VDD automatically through the use of a pull up resistor, which is usually about, say 10 kilo ohm or so. So basically what happens then is that if, for instance, none of the endpoints that are connected to this output are pulling down, in other words, none of them are trying to transmit a 0 on the wire or to set the wire to 0, then each one of these transistors being turned off is equivalent to about a mega ohm resistance. And this creates a voltage divider on this shared signal that is dividing the voltage, the 5-volt voltage, between a 10 kilo ohm pull up and essentially a 500 kilo ohm pull down resistance. And so that would create a small voltage drop. You'd have about 4.9 volts or so on this wire resulting from that. And obviously that number would drop even further the more devices that you connect to this wire. But I think in reality, when these transistors are turned off, that they're even more than a mega ohm of equivalent resistance. Now, on the other hand, if one of the devices attempts to pull this shared connection down to 0, to send a 0 out over this shared wire, that would create a pull down resistance of 1 ohm. You'd still have the pull up resistance of, say, 10 kilo ohms, and that would give you an equivalent. The equivalent resistance, as I mentioned, would be 1 ohm being pulled down, and that would create a voltage divider that would divide 10 kilo ohms and 1 ohm. So you get about half a milliamp of current that would flow through the pull up resistor down through the transistor here, and you would still get a voltage level there that is very low, very close to 0. So it would effectively be grounded. So the disadvantage here is that you get some leakage current through the pull up resistor whenever any device pulls the shared wire down to ground. All right, one way to solve this problem is to use an open drain style interface where each of the endpoints connected to the wire have only a pull down transistor. And then there's also a pull up resistor that connects the shared wire directly through a resistor with a value of about 10 kilo ohms or so up to the power supply. That way, if none of the devices outputting to that wire are pulling the output down, then the natural state of the wire will be a 1 value, because you end up with a voltage divider that's essentially dividing the bus between the shared connection between a 10 kilo ohm pull up resistor and 2 transistors that are turned off, which have about a mega ohm or so equivalent resistance that would be pulling down. So the equivalent resistance of these 2 transistors in parallel that are turned off, that are connected to ground, is about a mega ohm. So, is a half a mega ohm, because there's 2 of them connected in parallel. So you've got a divider that is an equivalent resistance up to VDD of 10 kilo ohms, equivalent resistance down to ground about 500 kilo ohms. So you'll end up with a small voltage drop, but only about 1/10 of a volt. So, on a 5-volt system like the one we use, that'll be about 4.9 volts. So basically that means that if no one's pulling down, you'll have 4.9 volts or so on this shared connection, so it'll look like a 1. Right? On the other hand, if one of the devices does turn its pull down transistor on, that will give an equivalent resistance down to ground of about an ohm. So now we have a voltage divider dividing a 10 kilo ohm rather pull up resistor and a 1 ohm pull down resistor. So you'll end up with near 0 volts, but you will get some drainage current of about half a milliamp or so down through that pull up resistor. Now, if both devices connected to the shared wire both attempt to simultaneously pull the output down, the effective resistance of two of those on transistors in parallel is about a half an ohm, which will create a very similar sort of voltage divider. So the voltage will still be 0, but the leakage current will only double at about 1 milliamp or so, divided, between the two legs, between the two transistors there or so, depending on how close their equivalent resistance is. So that's not catastrophic. And if that does happen, there's a way to detect that, because you can have another gate that checks for input immediately before you decide to pull down. Okay, so that's the style of interface that I2C uses. I2C is a 2-wire interface. In fact, it's called the 2-wire interface in the documentation for the Atmel products. There's actually, it uses 2 shared wires that are shared amongst all of the endpoints that are on the bus, both of which use the open drain style connection and have pull-up resistors to VDD. This allows I2C to be a multi-master bus, because any of these devices can drive both of these wires because of this open drain technique. The 2 wires are called SDA, which stands for serial data, and SCL, which stands for serial clock. Okay, so like SPI, whenever a transaction takes place, there's a master and a slave, where the master initiates the transaction and the slave receives it or responds to it. The word size is 8 bits, like SPI, generally speaking. Unlike SPI, I2C is unidirectional, meaning that only one side of the connection can send a bit at a time. Also, I2C is always sends the most significant bit first, unlike SPI, where that was configurable. I2C, as I mentioned, is a multi-master bus, so any of the endpoints can be a master. And also, SPI, remember, really just defined a way to exchange a byte between the master and slave. So when we wanted to do read and write operations, we kind of had to build that functionality on top of this exchanging business. And it was a little awkward too, because when you did a read or a write, you would end up having one side sending a byte to the other that was disregarded, that was a dummy byte, which was kind of awkward. So with I2C, every I2C transaction is a read or write. The read or write functionality is built into the protocol. It's not something that's kind of added on like it was in SPI. Another nice thing about I2C is that every time an address or a data word is sent from one side to the other, there's the other side who receives that word is able to acknowledge reception, which allows for some potential for error recovery, or at least error detection. So how do you claim mastership of the bus? You send a start bit. Remember that the SCL and SDA wires are naturally in a high state because of the pull-up resistor. So if I want to initiate a transaction, I want to become a master, I need only to pull down SDA. So I need a falling edge on SDA. So remember, SCA will still be high. SDA is pulled low. That signifies my intent to become a master. and that's also referred to as a start bit. It's a little confusing though, because it's not really a bit, but it's a transition. It's a high to low transition of SDA. So this is the timing diagram that shows that. So as I mentioned, both signals will be high by default, or when the bus is idle. To initiate a transaction, the presumed master will pull down SDA, and shortly after that, it will pull down SCL. Then it will send a 7-bit address from most significant bit to least significant bit. So to send the address, it will put each bit onto SDA, and then it will pulse the clock, rising edge, falling edge on the clock. That's how each bit is registered, or physically sent across the link. So that happens for 7 bits, A6 to A0. After A0, there's a read-write bit. If read-write is 1, in other words, if SDA is 1 during that slot where the read-write is expected, then that means that the master is reading. So 1 is read, 0 is write. Now, after those 8 bits total, 7 address bits, 1 read-write bit, the device that at that point is expected to take control of SDA is the slave. So the master relinquishes control of SDA, but the master then pulses SCL. That is basically clocking in a bit from the slave, which is an acknowledgement. That acknowledgement flag, or the value of SDA during that time slot, is a 0 for an acknowledge, and is a 1 for a not acknowledge, a NAC, right? So as shown here, a 1 in this position indicates that the address slave did not respond or was unable to process the request. Makes sense, because if it was unable to respond, then that would be a 0 there, right? Because again, SDA would naturally be pulled up to 1 if the slave wasn't pulling it down. So it would take the slave to pull that down to basically say, I'm here and I received your address. So 1 is a NAC and 0 is a ACK, right? Okay, so now at that point, things will change depending on if it's a read or write. If it's a read operation, meaning that the read was 1, over here the read bit was 1, then the slave will then take over control of SDA. The master will only pulse the clock 8 times to read in each of the 8 bits, the 8-bit word from the slave, which would be the contents of the read. And then the 9th pulse in this phase of the operation would be a way for the master this time to acknowledge the word that was received from the slave. And again, a 0 is an ACK and a 1 is a NAC. At which point the master has completed the transaction, and it enters what's called a stop bit by basically releasing SDA, but doing so after it releases SCL. So SCL goes high, and then you have a rising edge of SDA. So the stop condition is a rising edge on SDA after the rising edge of SCL. Okay? Okay, let's move on to 2 examples. On the top, we have the mastership gained by driving SDA low while SCL is high. So there's our start bit. And we expect the next 7 pulses of the clock to be clocking in the address, right? So let's count seven pulses. 1, 2, 3, 4, 5, 6, 7. Okay, and now if we read from right to left, which is most significant bit which least significant bit to most significant bit, you've got a 1, 1, 0, 1, right, which is 8 plus 3, 11B in hex, and 1, 1, 1, which is a 7. So 7B, so the address is 7B. Now, if we go past the address, 1, 2, 3, 4, 5, 6, 7. The next bit after the address would be the read-write bit, which in this case is being shown as 0, which is a write. So the master is writing to address 7B. The next bit is an acknowledgement bit. The acknowledgement is good. It's an ACK. Then the next 8 bits will be the word that the master is attempting to write into address 7B, which is going to be 1, 2, 3, 4, 5, 6, 7, 8 bits right there. So now again we'll read from right to left, least significant to most significant. 1, 0, 0, 0. So least significant hex digit is 1, and then 1, 1, 0, 0. So that would be a 3, 1. So the value that it's writing is 3, 1 in hex. And then the last bit position would be the slave acknowledging receipt of that word, which it acknowledges because it pulls SDA down during that pulse. And then the master releases the bus by releasing SCL and letting it go back high, and releasing SDA, letting it get back to high. So down in this example, in the bottom, we have the start condition. SDA gets pulled low while SCL is high. Then we have 7 bits of address. So 1, 2, 3, 4, 5, 6, 7. Reading from right to left, we've got 1, 1, 0, 1. Again, that's a B. And 0, 0, 0. So 0B is the address. 1, 2, 3, 4, 5, 6, 7, 8. The read or write flag is 1, meaning I'm trying to read. So the master is reading from address 0B. The slave acknowledges that address and read-write flag by pulling SDA down for the acknowledge here. And then the slave will continue driving SDA to send the contents of value 0B with a 1, 2, 3, 4, 5, 6, 7, 8. So again, reading from right to left is 0, 0, 0, 0. That's a 0, 0, 1, 1, 1, right? So that would be an E0 in hex. So the slave is responding with E0, and then the master acknowledges that by having SDA low during the last pulse, and then the master relinquishes the bus by releasing SCL followed by SDA and allowing them to be pulled up by the pull-up resistor back to high. And so that's it. That's all there is to I2C. We have already posted a quiz for I2C that is due on Friday. It is up on Dropbox right now. It's quiz 3, and we'll be posting the next lab, which will require you to do some work with I2C shortly. And also keep in mind that your lab 3 is due on Tuesday by midnight. That would be Tuesday, April 14th. So if you have any questions, don't hesitate to contact us, and thank you very much.